Ladies and gentlemen, you need to have a periodic table in front of you. If you need to borrow one of mine, please go ahead. Okay, but you're going to use them a lot today. Now, if you guys will recall, at the beginning of this chapter, I said to you that really starting in this chapter, we're going to start to see a lot less calculation and a lot more concepts explaining why, that kind of thing. You are really going to get a sense of that today, okay? And we're going to talk about what free response questions look like using these topics and not so much calculation. So we're going to talk about that a lot today. So we finished last class talking a lot about electron configuration. We're going to sort of wrap that up today. And the first thing that I just want to call your attention to, you learned this in Chem 1, okay? That elements that are in the same family, okay? So for example, all of your alkaline earth metals have similar chemical properties. Not the same, but similar. All right, they all react in similar ways. And ladies and gentlemen, to tie that in with what we were talking about last class, the reason that is because everything that's in the same family has an electron configuration that ends the same way. And if you think about it, all of your alkaline earth metals end in some number S2, right? Like 3s2, 4s2, 5s2, okay? Well, if things end with the same kind of electron configuration, then they're going to have similar chemical properties, okay? So I just wanted you all to be aware of that. Couple of terms that you might come across on the AP exam. I don't know if I use that term on my tests or not, but I just want you to be aware. If you ever see the term representative elements, what that means is any element in that S or P area of the periodic table, okay? So anything in groups 1, 2, 13, 14, 15, 16, 17, 18. Okay, those are called your representative elements. What do we call the elements in the middle of the table? Transition, okay? You can call them the transition metals, you can call them the transition elements. And then at the bottom of your periodic table, it's actually, the name is written there for you on your periodic table. That F block, the first row of F, they're called the lanthanide elements. And the second row is called the actinide elements. Yes, ma'am?
So when you say filling d orbitals, doesn't have to be like all the way full?
No,
okay.
It just means anything in the transition.
There?
Yeah.
Or, okay.
And guys, honestly, we don't really do much with these. Okay, we don't talk about them a lot, but just out of curiosity, I wonder if you know this. Are the elements down in this lanthanide and actinide series, are they metals, non-metals, metalloids? What are they? You got a 1 in 3 shot. What do you think? Yes? No?
Metal.
Correct. All right. They are metals. Now, are we going to ever do much with them? No, not really. Okay, but I just thought you should know that. So, this is where we're going to focus today. All right. We are going to be talking about energies and forces associated with electrons, okay? And we're going to tie that in with trends on the periodic table, okay? And a lot of today is going to be review from Chem 1. Maybe for some of you, especially those of you who are in honors, all of today will be review, okay? If you think about what an electron is experiencing, okay, I tried to demonstrate for you last class, although poorly, what an electron is going through, Okay, they're rotating in place, they're revolving around the nucleus, they're traveling in waves, there's a lot going on. Okay, so since electrons move at all, they are experiencing kinetic energy. Anything that moves has kinetic energy. Okay, here's something else they're experiencing. Let's look at this third one down here. Can you tell me why? Why is it that one electron with another one, why would two electrons experience a force of repulsion from one another? Tell me why.
They have the same charge.
Okay, exactly. They have the same charge. They're both negative. Like charges repel. Okay, so they're experiencing some potential energy from that force of repulsion. And then this is the one that we're really going to focus on today. Right? It has a very fancy name. It sounds much more complex than it actually is. It's called the effective nuclear charge. And guys, because that's kind of a lot to say, you have my permission on my test and on the AP exam. If you do not wish to write that all out because you're short on time or whatever, you have my permission to either abbreviate it like this. This is the variable for it, it's capital Z, EFF. Or you can abbreviate it as ENC, effective nuclear charge. That is okay. All right, the AP graders will know what you're talking about. So what is this? It's basically the force of attraction between the nucleus and an electron. Now think about that for a second. Why would an electron be attracted to the nucleus? Why? Yeah, go ahead.
Oh, because it's positively charged.
Okay, what in the nucleus, everybody, is making the nucleus positive? Protons. Okay, so opposite charges attract, negative electron, positive nucleus. They're going to be attracted to each other. Now think about mass and size. How does the size of an electron compare to the size of the nucleus? Way smaller, like magnitudes upon magnitudes smaller. So think about that for a second, especially physics people. You have a giant nucleus and a teeny tiny little electron. Is that electron feeling a strong attraction or a weak attraction to the nucleus?
Very strong.
Very strong. Very, very strong. Okay. So if electrons are attracted to the nucleus very strongly because of this effective nuclear charge, how come atoms don't just collapse on themselves? Like if the electrons on the outside are so attracted to the thing on the middle, why don't atoms just implode? What's keeping that from happening? There's two parts to the why that doesn't happen. For those of you that are in physics, and maybe you've actually done this, I don't know if you do this in physics or not, but if you have a string and you have like a ball at the end of the string and you're swinging it around in a circle. Oh, really? Oh, okay, you did it today. There you go. What is it about whatever it is that you're swinging around, whether it's a ball, a cup of water, an electron, whatever, what is it that makes the ball want to move away from you? The centripetal force is actually the force of you continuing to pull that ball in. But what is it that makes the ball want to fly off in a direction? Momentum. Okay? And guys, it's the same situation with electrons. They have momentum. They're moving around. The momentum of that electron wants to, it's like it wants to get away from that nucleus. And that's part of the reason why it doesn't implode. Now, can it get away? No, because that effective nuclear charge, which is basically equal to the centripetal force of this situation keeps it in orbit and prevents it from flying away. There is a second reason why your electrons do not collapse down and implode on itself. It has to do with this third situation right here. Think about there's not just one electron outside of the nucleus, there's multiple. If they collapse down, wouldn't all the electrons then be very close to each other? Yes? Do they like that? No, they do not. And so that's another reason that the atom doesn't just collapse. That force of repulsion is keeping them far enough apart. Okay? So 2 reasons there. And here's the deal, guys. We're going to talk about the trend on the periodic table for effective nuclear charge. And if you can understand that trend, everything else today will be very, very easy. All right? So let's talk about it. Okay? Let's talk about up and down in a column. Let's pick the elements. Let's look in group 1. Lithium versus cesium. Okay, group 1, lithium, cesium, same column. Can you tell me what is changing about the atoms as I move from lithium to sodium, potassium, rubidium, cesium? Every time I move down one row, what's happening to the atomic structure? Mark. Okay. Every time I move from one row down to the next, I am gaining another filled energy level. Okay. Well, I want you to imagine that I am the nucleus, because of course I am the center of the universe. Okay. I am the nucleus and you guys are all electrons. And I'm shouting at you. Okay, I'm mad at you. So I'm shouting at you. And you're kind of freaked out, so you just keep backing up, okay? Because you're like, oh, I don't know what she's doing. Why is she yelling? So I'm just going to keep backing up, okay? If you continue to move further away from me, is my voice in your ear getting louder, softer, or staying the same? Softer. It's getting softer. Same situation here. Those valence electrons, as you move from the top of a column down to the bottom, increasing number of energy levels, okay, the electrons are further and further and further away from the nucleus, so that effective nuclear charge that they are experiencing is getting weaker and weaker and weaker and weaker. Okay? Does that make sense? Okay, so lithium versus cesium. Which element is experiencing a stronger effective nuclear charge? Which one, everybody?
Lithium.
Lithium. And if you were asked to explain why, which you will, okay, you would say because lithium has fewer filled energy levels. Let's now talk about from left to right. Okay, so in a horizontal row on the periodic table. This one is a little bit more complex. Let's pick the third row on the periodic table. So period 3. Let's compare sodium and chlorine. Okay, they are on the same row on the periodic table, which really means in terms of atomic structure, they have the same number of, or what is the same about them? Same number of energy levels. Same valence energy level. It's energy level 3. So, are the valence electrons for sodium versus chlorine, are they really any further away from the nucleus? No. Okay. So imagine we have 2 people. Again, I'm shouting at you. I'm shouting at 2 different people, and they are exactly the same distance away from me. What is changing as we move from sodium to magnesium to aluminum to silicon, phosphorus, sulfur to chlorine.
More people getting
Greater number of protons in the nucleus, okay? Let's go back to my shouting analogy. I'm shouting at two people who are the same distance, but if one person is sodium and the other person is chlorine, I'm shouting a lot louder at the chlorine person. So they are hearing me a lot louder than the sodium person. Okay? As we move left to right, even though the valence electrons are on the same energy level, so the distance from the nucleus is not increasing, this pull from the nucleus is getting stronger on the right-hand side because additional number of protons means a stronger effective nuclear charge, a stronger pull. Okay? So, you tell me, sodium versus chlorine, which one has the stronger effective nuclear charge? Chlorine. If I were to ask you why, which I will, am I dropping enough hints? Okay. This one you have to say two things to get full credit. You have to say that they have the same number of energy levels. And then you have to explain something about how chlorine has a greater number of protons, which means a stronger effective nuclear charge. Okay? So up and down, all you have to talk about is number of filled energy levels. Left to right, you have to talk about how they have the same number of energy levels, but additional protons lead to a stronger effective nuclear charge. So last class, somebody asked, as you move down a group, someone raised their hand and said, well, as you move down a group, aren't you also increasing the number of protons? So, shouldn't it also be getting stronger as we move top to bottom? But distance from the nucleus makes a bigger difference than additional protons. Okay? I'm glad you asked that. Okay? Now, when you took Chem 1, you guys learned a whole bunch of different periodic trends. You learned about ionization energy, electronegativity, atomic radius, ionic radius. Some of you may have even talked about electron affinity. There's a whole bunch of different trends. But here is the good news. If you can understand that trend that we just talked about with effective nuclear charge, everything else, all the other trends come from effective nuclear charge, so it's much easier to understand. And for whatever reason, the College Board has decided of all the periodic trends, this is the most important one. I don't know why. This is the one they always ask about. All right. Will you ever see a question on atomic radius? Yeah, probably. But this is the one that they ask the most. Okay? So let's review what it means. Ionization energy. The energy required to remove an electron. Okay? Well, let's think about the trends. Okay? And for the moment, don't cross it out or anything, but ignore the word first. Just for the moment, I'll explain what that means a little bit later today. Okay? Before I, put up the answers to this trend, let's try and figure it out for ourselves. Let's think up and down in a column. Let's use the same ones we used before. Lithium versus cesium. Remind me, which one has the weaker effective nuclear charge? Cesium. And why is that?
Because there are more energy levels.
Because it has more filled energy levels. Okay. So which one would it be easier to take an electron away from? Cesium. Okay. So sometimes you'll have questions that will like give you a statement and you have to explain why the statement is true. It might say something like, cesium has a lower ionization energy than lithium. Explain. Right? You would say, cesium has a weaker effective nuclear charge because it has more filled energy levels. Period. Okay. So ionization, that energy, decreases as you move down a group. Okay, try to avoid saying things like, it's easier to remove an electron. Better is to say, it takes less energy to remove. Okay. Let's talk left to right. Sodium versus chlorine. Which one has the stronger effective nuclear charge? Chlorine. So which one of those two would it be more difficult to take an electron from? Chlorine. Okay, so maybe you're given a statement, chlorine has a higher ionization energy than sodium. Explain. What are you going to say? This is that two-part answer. What's the first part? Okay, they occupy the same energy level and
More protons.
chlorine has more protons and thus
Has a
stronger ENC. Okay, great. So ionization energy decreases as you move down a group and increases from left to right. Okay. And by the way, I should have asked you this before I even got to this ionization energy slide. Which element on the periodic table should have the strongest effective nuclear charge? Helium. Which would have the weakest? Francium. Francium. Okay? Now, ladies and gentlemen, what is on the next two slides, do not try to write it all down. Okay? It is the why that we just talked about. What I'm hoping is that you wrote down your own notes in your own words, but this is actually, you know, the real reason. So if we're talking up and down, we've got more and more energy levels, greater distance from the nucleus, okay, which leads to a weaker or lower, you can say either, effective nuclear charge. If we're talking left to right, we're on the same energy level, but additional protons lead to a stronger effective nuclear charge. Okay. Now, let's go back and let me explain why that word is there. This means the energy required to remove one electron. There is such a thing as a second ionization energy, and let me be clear about this. This does not mean the energy required to take 2 electrons. That is not what it means. This means one has already been taken. How much energy does it take to remove another one? And you can have third ionization, fourth, fifth, sixth, and so on and so on and so on. Okay? And ladies and gentlemen, there is a relationship here, and I don't get to say this very often, that holds true for every single element, no matter what element it is, no matter where it is, no exceptions. I don't get to say that very often. Whatever the number, whatever that element's first ionization energy is, the second will always be bigger. And the third will always be bigger. If there was a fourth, it'll be bigger than the third. A fifth will be bigger than the fourth, and so on and so on and so on. Okay? For example, okay, I want you to look at these numbers. And these are real numbers, okay? I didn't just make these up. For the element magnesium, first ionization, second, third, okay? I want you all to first of all notice that they are all positive. What does a positive energy mean to you? Endothermic, what does endothermic mean? Heat is absorbed, heat is required. It takes energy to remove an electron from anything. Atoms want to hold on to their electrons. They don't want to let them go. Okay? There are two things to notice here. Number one, did you all notice, just like what I said on the previous slide, that each number is progressively getting larger? Do you see that? Okay. Why do you think that is? You've taken away one electron. Why does it take so much more to remove another, and then even more than that to remove a third? Every time one electron is removed, okay, it's like a tug of war. The amount of protons is staying the same, but the number of electrons on the electron team is decreasing, and they're losing the tug of war. The protons are winning. The effective nuclear charge is getting stronger and stronger and stronger, okay? One of my former colleagues that I used to teach with had this analogy, and it's sort of depressing, but I think it works perfectly. Let's use carbon as an example. How many valence electrons does carbon have? 4, okay. I want you to imagine the nucleus of carbon as like a mother, and the 4 valence electrons are her children. Okay? Horrible situation, one of the children is abducted, which is like my worst fear in life is child abduction. Anyway, okay? One of her 4 children is abducted. Don't you think that she's going to hold on to her remaining 3 a little bit tighter than she was before? And God forbid, a second child is abducted. Those 2 that are left, she's never letting them out of her sight. Okay? It's the same situation here. Okay? That love for the electrons gets stronger and stronger and stronger. Now, do not on a test say, well, because mothers love their children. No. Okay? You can't use that. You have to use what I call AP Chem lingo. These energies get progressively larger because the effective nuclear charge is getting stronger or is increasing. Now, please, if you would, put your finger on where magnesium is. Pay attention to where you have just put your finger. And tell me, don't answer immediately, why are we seeing not just an increase, but a big jump from here to here?
Because by the time you've taken away 2 electrons,
Okay.
magnesium would have the same electron configuration as neon, which is a noble gas, which the outer energy level is full.
Okay.
So it takes a whole lot of energy to remove something from a full energy level.
Absolutely. Okay. Let's give her a golf clap. Okay. Or a loud clap, whatever. Okay. Can you tell me what type of electrons are these first 2? Valence. What kind of electron is that third one? Core. Okay. Here's how you explain that in a concise way. It takes more energy to remove a core electron from a full energy level than it does to remove a valence electron. Answer done. Do you want me to say it again? Okay. It takes more energy to remove a core electron from a full energy level than to remove a valence electron. Okay. Now, why am I paying so much attention to, how we say these things? Well, before you try some of these questions on your own, I want to talk to you just briefly about what these free response questions are going to look like. Because as I said, less and less calculation, more and more explanation. Ooh, that rhymes. Okay. So you're going to have statements given to you, and you will have to explain why the statements are true. This is not like AP Bio. AP Bio, their exam has an essay portion. We don't have essays in here. In fact, we don't even really, you could almost not even call it short answer. AP Chem has a sentence maximum number, okay? You have to be able to answer these questions, explain why, in 2 sentences or less. And I don't mean run-on sentences. Comma, and, semicolon. Okay? We're talking 2 complete thoughts, which you think, oh, that's awesome. I don't have to write that much. Let me tell you something, people, and I think your English teachers would agree. It is much harder to write in a very concise way than to go on and on and on and on and on and on. Okay? Here's the deal. When you take the AP exam, and this goes for my tests as well, I will read 2 sentences. I will not read beyond that. So you better put your right answer in those first 2 sentences. If you are a very verbal person and you like to go on and on and on and on, I'm not even reading it, so just stop writing. Okay? So, I'm going to focus a lot today on how to say these things in a very concise way. Okay? So, what I want you to do is I want you to pretend that this right here is a free response question. I have given you some information. Similar question, different element. This is aluminum. And I want you to explain 2 things. Number 1, why are all the energies successively getting larger? And number 2, why is there this big jump from here to here? Don't say it out loud. I want you to write it down. Okay? Pretend it's an AP question. You're using that AP Chem lingo. Keep it concise. Does it have to be in complete sentences? No, it doesn't. You are permitted to answer these questions with like bullet points. That's totally fine. They will read no more than 2 bullet points. Okay, let's try this out. Okay, remember the first part of this is, why is each ionization energy getting successively larger? Someone take a stab at it. Don't be afraid to be wrong. We're in the safe tree, the trust tree. We're in the nest. Come on, somebody take a shot at it. Kate, go for it.
Okay, so they get successively larger because the ENC increases due to the fact that there is less potential energy from the repulsion of other electrons.
Okay. All right, I'll take that. I can give you a more concise way to say it. Okay, although she did not exceed the 2-sentence maximum, so she's okay. All right, she said correctly, the energies get successively larger because the ENC is increasing. Okay, what I would say as for the because, like why is the ENC increasing? The proton to electron ratio is increasing. Remember I talked about that tug of war? Okay. With every successive removal of an electron, that proton to electron ratio is increasing. And that's really answering it in one sentence, so that's pretty good. Let's think about the second part. Why is there such a large increase from the third to the fourth? Somebody else take a stab at this one. Coral, try it.
Because aluminum has already lost all its valence electrons and it's harder to move forward.
Okay, correct. It's a core versus valence issue. The only thing I would change is instead of saying it's harder to, say more energy is required to remove a core electron from a what, everybody? From a full energy level. More energy is required to remove a core electron from a full energy level than a valence electron. Okay, very nice. The trap that I see some people fall into is they'll say something like, after aluminum has lost its 3 electrons, it is like neon. Well, like, I know what you're trying to say. It has the same number of electrons as neon, but it's not neon. It's aluminum. Okay, so just be careful with that. There's really no need to ever bring in the name of some noble gas into these explanations. Okay, so we just looked at 2 elements. Magnesium and aluminum. Let me just write some numbers down here. This was magnesium's first ionization energy. Aluminum. Okay, I just got those numbers from the 2 previous slides. Those are their first ionization energies. All right, let's kind of review here. True or false? Moving from magnesium to aluminum, we are moving from left to right. True, good, very good. Okay, true or false? As you move from left to right, ionization energy generally increases. True. So I've been lying to you? No, I haven't been lying to you.
About that.
Yes. I'm not ready yet. I'm not ready yet. Okay? Ladies and gentlemen, this is the essence of AP Chem right here. Here's a blanket statement. Here's a rule. Oh, but wait, there's a whole bunch of exceptions. Okay? That's like the essence of higher level chem. You've learned these blanket things, these big overarching rules and statements. Oh, but actually, okay? Just get used to that feeling of like Chem 1 was all a lie. No, it wasn't a lie. It just wasn't
The full truth.
it wasn't the full story, okay? Here is an exception to that ionization rule. Let me draw you a picture to aid in this explanation. Can you tell me, please, how many valence electrons does magnesium have?
2.
And what sublevel are they in?
3.
Right. Sorry. I had to think about that for a second. 3s. Whose rule explains why I just drew those arrows up, down? Poly! Poly exclusion. Aluminum has 3 valence electrons. And ladies and gentlemen, remember, ionization energy means removal of an electron. I have circled the electron that is to be removed. I want you to look at that picture. And for the moment, don't worry about AP Chem lingo. Why do you think it's easier, slightly, to take this electron than that? Don't worry about lingo for now. What do you think?
It's similar to the way that taking away a valence electron is easier than a core electron because
Okay.
the p orbital is not full,
Okay.
so it's easier to remove something from an unfilled orbital than a filled one.
Okay. She said it's easier to remove something from an unfilled orbital than a full one. Absolutely right. Okay. Would you all agree that this sublevel, the 3s sublevel, would you agree that it is full right here with those two electrons? Yep. Okay. How would you describe this sublevel? It's not full. It's not even half full. It's not empty. There's one electron in it. 1/6. True. How about we just say it's partially filled? Okay. Partially empty. Don't say. Let's be on the bright side. No, not pessimists. Optimists. Okay. Here is the AP Chem lingo. Are you ready? Less energy is required. Don't say it's easier. You say less energy is required to remove an electron from a partially filled sublevel than from a full sublevel. You want me to say it again? Okay. Less energy is required to remove an electron from a partially filled sublevel than from a full sublevel. And if this were a free response question and I'm trying to answer this, guys, pictures speak 1,000 words. I would draw this because guess what? Pictures don't count against your precious word count. All right? If you draw this, that saves you the time, whatever, of having to say an electron from 3p, an electron from 3s. You've drawn it. Okay? It cuts down on the number of words you have to say. All right? Okay? So, hold on. There, on this boundary, ladies and gentlemen, from groups 2 to 13, that is an exception to the ionization rule. You would see the exact same phenomenon going from beryllium to boron. When you get a little bit lower where the transition metals are, things start to get a little fuzzy, like from calcium to gallium, for example, but in general, you still see this exception. Coral, you had a question.
Yeah. If you were to draw the picture,
Mhm.
would you have to start at like 1s or could you just
No.
start?
You can just draw the valence electrons.
Okay.
That would be fine. All right. So, groups 2 to 13. There is another place where there's an exception. We're going to compare these two elements. Nitrogen and oxygen. And I don't have numbers, ionization energies for this, so I'm just going to make it up. I'm making up numbers. Let's say nitrogen has an ionization energy of 475. Oxygen (406). Let me again draw you a picture. How many valence electrons does nitrogen have? 5. And this is in 2s. This is 2p. Ladies and gentlemen, whose rule explains why I'm drawing the arrows up, up, up? Hund's rule. We don't like people. Right. We're antisocial beings. And I'm going to, again, circle the electron to be removed. Now that you know the lingo, Can you explain this anomaly in the general trend? We'll treat it like a fill in the blank. Okay? Less energy is required to remove an electron from, how would you describe this situation? A partially filled sublevel than a, how about half filled? Isn't it? Don't you agree? Isn't it exactly half filled here? Okay. Less energy is required to remove an electron from a partially filled sublevel than from a half filled sublevel. Yes, ma'am. The take-home message here, ladies and gentlemen, is full sublevels and half sublevels are considered to be very energetically stable, and they don't like to be messed with. Okay? They're in their happy place. I'm using a lot of terms you don't want to use on a test. Okay? Please don't describe elements as being in their happy place. Okay? And another thing that I see a lot of people fall into the trap of is saying things like nitrogen wants or oxygen doesn't want. Okay? They don't have feelings. You can't say that. So on this boundary, 15 to 16, you see this phenomenon. What other elements on that boundary? Where else would you see this? Phosphorus to sulfur. Do we all know the names of the elements below those? Arsenic, selenium. Okay, antimony to tellurium. Bismuth to polonium. Very nice. Ladies and gentlemen, this is a practice question for you. I have given you 3 different electron configurations for 3 different elements. 2 separate questions, which, okay, fine, you can take 2 sentences for each one. This one says, which atom has the largest first ionization energy? And be prepared to explain why. And let me reword the second question because it's a little confusing. Which one would have a large jump from its first ionization to its second ionization energy? Try it on your own first, and then we'll go over it as a class. All right, first of all, tell me, what element is that? Neon. Okay, neon. And then the next one? Sodium. All right, sodium, and then magnesium. Okay. In AP Chem lingo, somebody take a shot at it. Which one of these has the largest first ionization energy and why? The answer to the first question is neon. Okay? And all you have to say is that it takes the most amount of energy to pull an electron from a full, not just full sublevel, from a full energy level. And that's all you have to say. Neon requires the largest first ionization energy because it requires a great deal of energy to remove an electron from a full energy level. Let's think about the second question. Which one has the biggest jump between the first and the second? Okay, sodium will have that big jump between first and second. And here's how you say this in a concise way. Removal of a second electron from sodium is the removal of a core electron from a full energy level, which requires a lot of energy. I said it in one sentence. Boom! Guys, electron affinity is a term that you're really not going to see very often, but I just want you to know what the term means, okay? And it's essentially the opposite of ionization energy. So let's kind of wrap this up. Ionization energy was the energy required to remove an electron. This is the energy associated when an electron is added. Okay? So what you're going to end up seeing is a lot of elements that have very exothermic electron affinities. Can you tell me, can you think of a family on the periodic table? And I'm going to use a word that, again, you would not use on a test. Can you tell me a family of elements that would really like to gain one electron? Why would the halogens like that? Yeah, that would leave them with a full energy level. So guys, the halogens, for example, have very, very exothermic, very negative electron affinities, because that's a situation they would really, really like to have. Can you give me a family of elements that would really, really, really not like to have an additional electron? Okay, yes, noble gases, but even more than them. The alkali metals. Okay, so what you tend to see, non-metals will have very negative electron affinities, and to put that into your own words in your brain, they really like to take on one more electron, whereas metals don't want to do that. All they want to do is get rid of their electrons. That's why metals form positive ions and non-metals form negative ions. Oh. Okay. But again, are you going to see a lot of questions on this? No. I just wanted you to know what the term means. All right. The last thing, and this is so quick because we've already explained all of it. How many of you in Chem 1 learned the trend in size radius with a snowman?
Yeah.
Okay? Since you are AP Chem geniuses, tell me, why is it that as you move down a group, the radius gets larger in AP Chem lingo? And you can't say because of the snowman. Do not say that on a test.
There are more energy levels.
There you go. One sentence, not even two sentences. Atomic radius increases as you move down a group because you have increasing number of filled energy levels. Period. Okay, then some jerk comes along and knocks the snowman down. Tell me please, in AP Chem lingo, why is this happening? This is a two-part answer, remember? What do they have in common?
The snowman fell over.
No, the snowman did not fall over. You can't say that. Okay, part one, all elements in the same row have the same number of energy levels. And Will, what's the second part? As you move from left to right, there's increasing number of protons, which, don't call it the pull, which increases the effective nuclear charge. Okay? And this just has some general stuff which we've already talked about. Make sure you are comfortable with all of your family names, alkali metals, alkaline earth metals. Can you all very quickly, give me some general characteristics of metals? Go.
Conductors.
Malleable. Good conductors of what?
Electricity.
Electricity and heat. What else?
Ductile.
Ductile.
Malleable.
Shiny. How about
Malleable.
lustrous? That's a better word than shiny. Okay, what else?
Are they
How about melting points? High, low?
high?
High. Okay. Super fast. Give me some characteristics of nonmetals.
Weak conductors.
Okay, weak conductors. Mostly gases at room temperature, not lustrous. How about dull? Sure.
Low melting point.
Form anions, low melting points. You get the gist. Okay. We're done, everybody.